Hi, I'm Yanru Lu. I'm from the Academia Sinica. Thanks for inviting me. I'm going to introduce our work, which utilizes the broad phonetic information to help the speech enhancement get better results. When we listen to the noisy speech signal, knowing what the speech content is can help us to reduce the background noise and retrieve the pure speech signal easily. However, if we use the well-known phoneme-based acoustic model to extract the phoneme content, the recognition result will be unreliable in high noisy condition and brings the error information to the SE model. To solve this problem, we use the BPC-based acoustic model instead. The accuracy of the BPCs are much higher than that of phonemes because the BPC-based acoustic model only need to separate the signal into few classes, but not all of the phonemes. As a result, the phonetic information which is provided by the BPC-based acoustic model can be more accurate and guide the SE process under very noisy conditions. The code of our work is on the GitHub. You can follow it by this QR code. We will start with introducing the broad phonetic classes. The idea is that we cluster all of the phonemes into several groups and make sure that the similar features can be found among the phonemes in the same groups. To achieve that, we do the clustering through knowledge-based and data-driven method. There are two knowledge-based separating methods are used in our work, called place of articulation and the manner of articulation. Place of articulation means where we pronounce the phone, like dental or plateau. It is the place where we obstruct the airstream to form the consonants. The manner of articulation is how we pronounce the phone, like frictive, glides, or affricates. The same abstract way are classified into same classes. As mentioned before, the phonemes in the same cluster should share some of the similar features. We can find out the similarity in the graph below. This graph is from a well-known textbook, A Course in Phonetic, showing that the phonemes which are pronounced by the same way will generate similar waveforms in their shape. As a result, even if the SE model only knows that the speech signal belongs to which of the BPCs, it can help for identifying the correct speech signal from the noisy speech waveform. On the other hand, we can use the data-driven way to separate the phonemes. The confusion metrics are constructed by counting the misclassified recognition results of an acoustic model. If two phonemes are usually misclassified into the same results, they are considered as sharing the similar features, and they will be conflated into a new group. The combination step is iteratively conducted on all of the groups and phonemes to reduce the total number. This process will stop when the classes number reach the goal. This method is developed from the paper below, and we take it as one of the BPC classified methods to extract the posterogram for guiding the SE model. In our system, first, extracting the speech content, we train an acoustic model to predict the posterogram. However, for assuring that the acoustic model can perform well even in the noisy condition, we use the BPC acoustic model instead. The BPC acoustic model only need to predict that what the class is, making the task easier, so the extracted BPC posterogram will not contain any information of what the phone is, but only the BPC-related information. Due to the dimension of the BPC posterogram are still much larger than the noisy spectrogram, an autoencoder is used to reduce its dimension. The autoencoder consists of 3 fully connected layers with descending dimension in the encoder network, and the decoder network is symmetric to it. The BPC posterogram is sent into the autoencoder to extract the bottleneck feature. Then, the features are concatenated with the noisy spectrogram as the input of the speech enhancement model For providing the broad speech content information, we choose the transformer as the speech enhancement model. In the transformer, 4 one-dimensional convolutional layers are used to encode the input feature. We set the number of the attention block n to 8. Each of the attention block is formed by the multi-head self-attention element, consists of 8 heads and the 2 layers feed-forward network. The transformer network are trained to predict the clean spectrogram from the concatenated inputs of the noisy spectrogram and the broad speech content information. In our experiment, we use the TIMIT dataset for training and testing. The training data contains 3,696 clean utterances and corrupted with 100 noise type and 32 different SNR levels. For the acoustic model, we only use the clean utterances for training, and for the XE model, this is trained by the noisy dataset. In testing, 192 utterances in TIMIT core testsets are used. 5 unseen noise type and 5 SNR levels are added into all the utterances for testing. There are several experiment types in our work. The different notation represent the acoustic model recognition target. The mono experiment means the acoustic model is trained to predict the original phoneme for comparison. BPCD means predicting the data-driven BPC. N means the manner of articulation, and the P is the place of articulation. The table are the recognition results from these acoustic models. In 0 decibel, the significant drop in the accuracy can be observed within the monophone experiment, while the accuracy of the BPCs are still acceptable. This graph visualizes the prediction results. The stars in the graph means deletion, and the red one means substitution or insertion. When the SNR is 10 decibel, the graph shows that both of the BPCs and the phonemes recognition results are corrected. But when the SNR is 0 decibel, the recognition results of the phonemes drop dramatically, while the accuracy of BPCs are still acceptable. The misrecognition phonemes will bring incorrect information that misguide the SE process. This is the speech enhancement results of our system. We use 2 scores to evaluate the performance of the SE models. STOI represent the intelligibility of the speech. PSQ means the quality of the speech. For the STOI scores, compared to the transformer baseline, the monophone results are slightly better in most of the conditions. However, when the noise is extremely high, the monophone posterogram would bring the erroneous information to the SE system and make the enhancement worse. By contrast, due to the high accuracy, the BPC posterogram can help the SE system enhance better even in the very noisy condition. They also perform better than the transformer and monophone under each condition. The average PSQ scores show the similar results. All of the 3 BPCs enhance better than the mono experiment. The best results are generated by the BPPG-M. It means the manner of articulation, which has the most distinct feature between different classes as mentioned before. So, the BPC posterogram can bring efficient information for the SE system even in the high noise condition and improve its robustness. To further identify the effects of phoneme and BPC, we conduct an additional experiment by using the ground truth label. The original content feature from the TIMIT corpus is using the posterogram information. More specifically, in the ground truth experiment, the input to the autoencoder in our SE system is the 1/2 factor, whose dimension is the number of monophone or BPCs classes. Here we use the manner of articulation as a representation for BPC. This set of results was denoted as GT-PPG and GT-BPPG. From the results, BPPG still perform obviously better than PPG, suggesting that BPC may be more suitable than phoneme. to improve the SE performance further. In this paper, we propose to use the BPC information to guide the SE process to achieve better denoising performance. 3 clustering criteria are investigated, and the results confirm that incorporating the BPC information can make the SE's performance improve notably over different SNR conditions. The performance even outperformed the monophone PPG SE system. From the ground truth results, we know that there are still rooms for further improvement. We will further explore how to efficiently use this BPC information for the SE task in the future study. The code of the BPC SE are on the GitHub. You can follow it by the QR code. Thank you for listening.